So I'm not going to show, all I'll show is just one equation, and this is really kind of a new development that allows us to do this type of coupling. What I want to talk to first is this table here. One of the challenges when you get out of a structural mechanics code and you move into a fire code is that you're dealing with a set of physics that aren't equal. So for example, within the codes, you can simulate gravity force. In our fire code, we can't simulate structural deformations. That's really in the regime of the structural dynamics code. Both codes are designed to conserve mass and momentum. Both have methods for conserving energy. If we come down here to the bottom, our chemical reactant flows, we can only manage those within our fire code. Turbulence is really only able to simulate in the fire code and surface tension. So what we've had to do is develop methodologies to transition from one code, which is lacking some physics, into another code which needs physics that was lacking in the previous code, but also can't take physics from the other. And one of the critical realizations was that by defining a dimensionless drop separation distance in our Presto SPH simulations, we can determine an appropriate way to stage our transfers. And staging the transfers actually makes sense from the perspective of you want to be able to, in reality, what you have is you have this core of the impact. And this core of the impact is fairly well simulated by the structural mechanics code. But as you move to later and later times, you start to move into the physics regime of the fire code more and more. And that basically is consistent with your separation distance between your particles divided by some characteristic distance, which in this case we've been using the drop diameter. So this has been a free parameter that we've used in our simulations. Let's see, we've been initializing our output from our structural dynamics code as spheres, the same type of elements as they were in the structural mechanics code. We're ignoring the aluminum as it's transitioning out of our structural mechanics code into the fire code. And again, we're assuming that all drops stick when they impact the surface. Our simulation matrix looks like this. This is fairly complicated, but I'm going to walk you through it so you'll understand the terminology here. We basically had two different levels of mesh refinement in our fire code, a coarse and a medium. This is about 500,000, and this is 3-ish million elements. Our Presto mesh had four levels of refinement, varying from coarse, medium, fine to extra fine. Coarse being a little less than 1,000 elements, and extra fine being on the order of 50,000 elements. Varying between those. We used two different approximations for transitioning between the codes. One is we did not use temporal staging, the other one is that we did. And we used various dimensionless spacings to determine the point at which the particles transferred between the codes. So ostensibly, all of our calculations are the same because these are essentially the same input conditions. Really, all we're varying is our resolution, temporal resolution, and then our length scale resolution for the problem. So, therefore, the differences that we're finding in all the simulations that are presented in this talk are due to discretization and staging. So, again, our cases are designed. The first letter is coarse or medium for our Fuego mesh. The second letter is coarse, medium, or fine or extra fine for our Presto mesh. Our temporal, whether or not we're temporally staged, S for staged and U for unstaged, and then the dimensionless spacing is the last number. So what I've plotted here is the airborne liquid mass versus time in these scenarios. So you can see that our reactions in these scenarios take place predominantly within about a second time. Our mass starts out at about 8 kilograms and decreases down to fairly quickly as it combusts down to about 10% of the original mass by about a second. What you can't see here is you can't really tell what it's really hard to pick from this what everything's doing. So in the next few view graphs, what I'll show are bar charts that help illustrate some of the trends that we found in running these simulations. So basically what we're looking at here, this is basically the time at which you have a half of the liquid mass left in drops in the calculation, and then this is the time at which a quarter of the mass is left in the drops. These are indicative of the progress of the evaporation and combustion. There is some monotonic trending, except for this coarse simulation. There's a general decrease in the amount of mass remaining in the system, or the speed at which the mass is consumed for our Presto mesh changes. We also find that for our finer fire code meshes, that there tends to be a little bit faster combustion taking place. We also find that there's a slight trend. It's monotonic with our dimensionless spacing assumption, but it doesn't seem to be nearly as significant, I guess, as our fire code mesh resolution. We get reasonable accuracies among all of these with our averages and standard deviations. Our standard deviations being significantly smaller than the averages. I've plotted on this plot the number of particles simulated in the system for the varying cases. Unfortunately, we're running out of space here, and I'm getting pretty tight on time, I guess. One thing of note, we didn't expect this particular case. This is the case where we allowed transfers over a longer period of time. We didn't expect that to be a significant parameter, but here we were able to show that it actually is a significant parameter in the outcome. Since I guess red means I'm out of time, one last thing I want to show, I do want to show the videos, these impacts, before I end. So, I'll show the course simulation first. This is the structural dynamics impact, and then this is the fireball prediction. Following that, our drops here are colored according to their size, and then the fire is represented essentially by it's essentially color coded based on color, and we use a custom coloring scheme to make it look like a fire. That's not really representative. It looks like there's certain things like that, but our finer, our medium mesh on the Fuego side actually tends to resolve a lot of the dynamics in the fireball a lot better. And so, at least from this perspective, having a higher resolution on the fire side gives you a much more visually representative prediction. So, let me just go to my conclusions and then we'll give time for questions. So we believe we have a new capability to predict fires from impact scenarios that involves a code coupling. The work that I presented here builds on the validation that we've previously done. Our transfer coupling methodologies and discretization assumptions were evaluated in this work. For notional impact, we find that our prediction results are fairly similar for all cases, but there is some trending that is attributable to our model discretization assumptions. Magnitude of the standard deviations that we present give a sense for the accuracy that we can obtain from these types of calculations. At least at this point, I think analysis is best performed with a variety of assumptions to give a sense for what the range of answers are. So, thank you.
Thank you for your nice presentation. We have time for one question. Only one question, please.
You go ahead. My question is just, if I have this right, the velocity field from the combustion doesn't come into your calculation. You just have the impact into a quiescent environment, and so any effect that has, I assume it's small, is not modeled. Is that right?
Well, it's not modeled within the structural mechanics prediction. But once we transfer over our structural mechanics prediction into our fire code, then you do get the responsive the flows. So the problem is how do you initialize the flow of this object before it's moving as it's impacting? And that's something that we haven't really addressed yet. But certainly once the impact does occur, we start to link in the fluid mechanics of the liquids as they're transitioning around the regime. Yes, there is a direct coupling between the liquid phase and the gas phase.
Okay, thank you very much.